Welcome to Module 4 of the Ruckus Wireless Fundamentals course. In this module, we will define and discuss the units of measure related to Wi-Fi signals. We're also going to show where those measurements are taken and how to apply those measurements using RF math. After completing this lesson, you should be able to understand absolute and relative units of measure, use basic RF math to calculate RF power levels using the rule of tens and threes, apply the basic concepts of RF mathematics and measurement, as well as calculate link budgets, and understand signal-to-noise ratio and receive signal strength indicator values. Understanding the power used in Wi-Fi ensures that you will be able to meet coverage requirements and stay within the laws that are in place within the regulatory domain in which you are deploying Wi-Fi. Units of power measurement are absolute power measurements. The watt, being the first we'll discuss, is a method of measuring the rate of energy transfer of a device. 1 watt is defined as the energy consumption rate of 1 joule per second. However, it's very rarely that you will be dealing with a watt in Wi-Fi. That much power is usually reserved for outdoor use and only in regulatory domains where the use of such amplitude is legal. Most of the power levels required for Wi-Fi are much lower, since Wi-Fi networks do not need a tremendous amount of power to transmit a signal over an acceptable distance indoors or outdoors. Therefore, we will use milliwatts instead. Milliwatts are 1/1000th of a watt. Consumer grade and even most small office, home office wireless devices may only offer between 30 milliwatts of output power up to 100 milliwatts of output power. This 100 milliwatts transmit power is before the antenna, so you must take care not to exceed the legal power output restrictions of the region within which you are deploying, since antennae are bidirectional passive amplifiers. In high-density deployments, you will find most APs are set to a much lower power level to reduce cell overlaps and co-channel interference. Decibels. Decibels are used to measure change. However, when using dBm, decibels measured, you are dealing with an absolute power measurement. Decibels measured is relative to 1 milliwatt. A decibel is 1/10 of a bell, so you could just as easily express that as a bell being 10 decibels. The radios used in Wi-Fi are able to both detect and process very weak signals. And when dealing with these weak signals, it is easier to refer to the received signal strength indicator values in dBm rather than in milliwatts. The transmitted signal loses strength as it propagates away from the transmitter. You could be transmitting at 100 milliwatts from an antenna, but due to the distance, noise, and the sensitivity of the receiving device, you will never receive at that signal wirelessly. Remember, the signal gets weaker exponentially as it propagates away from the transmitter. That 100 milliwatt signal will be received as a strength so weak by comparison that it has a negative decibels measured value, such as negative 80 dBm, the strength needed for basic connectivity. Within Wi-Fi, a relative measurement represents a change in power as an RF signal moves from one point to another point in space. The decibel is a comparative measurement value. It is a measurement of the difference between two power levels. For example, it is common to say that a certain power level is stronger or weaker than another when comparing RSSI values of neighboring access points. If you said a signal was 3 dB stronger than another, that would mean that signal is roughly twice as strong. This statement may be true, but does not tell us how strong either signal is in absolute measure. It's only a relative measure. You are simply comparing them to each other, like saying one melon is twice the size of another without actually saying anything about their actual sizes. As you learned earlier, a decibel is 1/10 of a bell. We use this measure in Wi-Fi for comparison of signal strengths, not absolute measure. dBi is a logarithmic measure of change in power referenced against an isotropic radiator. An isotropic radiator is spherically perfect in its radiation pattern, such as the energy emitted by the sun. Antenna gain is usually measured in dBi. Another measure you may see used in antenna description is dBd. This is a decibel measured against or relative to a half-wave dipole antenna. A dipole antenna is the proper name for what most people call an omnidirectional antenna. More often than not, you will see dBi used for antenna power. Either way, the rating of the antenna tells you how much change there will be in either the transmitted or received signal power, or the difference in what you're going to see when you're measuring. Both measures are relative and neither are absolute. For example, if you're using a transmit power of 50 milliwatts and you are using a 3 dBi or dBd gain antenna, you are doubling the power of the signal you are putting into the air. Conversely, if you are using an RF cable connected to a radio and to the antenna, the cable can introduce signal loss, and the cables are normally rated based upon the dBm or dBi loss in the cabling. Absolute power measurement represents the transmit amplitude of a signal or the received amplitude of an RF signal. This chart shows us a comparison of decibels measured to milliwatts. You can clearly see now why the use of dBm makes so much sense in Wi-Fi versus using the actual milliwatt values when discussing signal strength. Within the actual math used in calculating signal strength, we use logarithms as an industry to determine true values. Logarithms make it easier to quantify large changes in values instead of dealing with a decimal and lots of zeros. dBm, decibels measured, is an example of a logarithmic measure of power units. The intentional radiator and equivalent isotropically radiated power levels are two things that are really important for RF math calculations and making sure that you are in compliance with local regulatory domains. In RF math, there are a few terms you really need to understand. The transmitter and receiver are obviously the device that creates the signal and the device that receives the signal, respectively. For the math, you will need to understand two important terms for calculations and knowing where transmit powers are calculated. The first of these terms is the intentional radiator. In a wireless LAN transmission system, this is the point at which the antenna is connected to the radio or to the cable that leads to the radio. The RF signal from the transmitting radio may pass through connectors, cables, attenuators, amplifiers, and lightning arresters before it even gets to the antenna. All of these components impact the signal before it arrives at the antenna. The combination of these things is the signal that you are intentionally trying to send. Regulatory bodies have set legal power limits measured at this point, the intentional radiator, sometimes called the intentionally radiated power in regulations. The second term with which you need to be familiar is the equivalent isotropically radiated power, EIRP. It is the theoretical power that is delivered by an intentional radiator to an imaginary isotropic antenna that would produce an even distribution of RF power with the same amplitude actually experienced in the preferred direction of the antenna. All of that really means the power placed into the air measured at the tip of the antenna. Mathematically, it is the combination of the transmitted signal, all loss introduced by connectors such as pigtails or metal connectors, attenuators, lightning arresters, amplifiers, everything between the transmitter and the lead of the antenna that connects to the cable is the intentional radiator. All of that combined with the gain of the antenna is the equivalent isotropically radiated power. Relative power measurement. Now that we understand intentionally radiated power and equivalent isotropically radiated power, Let's talk about where the power is measured as well as the names of the measurement locations. The first will be taken at the transmitter and is an absolute measure. In this example, it is 100 milliwatts, or the equivalent to 20 decibels measured. The second will be the measurement of loss introduced by the cable and any connectors. Cables and connectors only introduce loss since they increase the amount of wired media the signal must traverse before striking the antenna. The media has some resistance in it, which introduces some loss into the transmission because there's resistance as the electric current goes through the medium. There's equipment that you can attach to the ends of cables to actually measure the true amount of intentionally radiated power the system is transferring to the antenna. So a measurement taken at the end of the cable which connects to the antenna is able to be measured and can be expressed in an absolute value. In the case it is 50 milliwatts or 17 dBm, the location is where the intentionally radiated power or IR is measured. It is also one of the locations that is regulated by governments around the world, how much power you can purposely put into an antenna. After the intentionally radiated power, antennas are attached and they are bidirectional passive amplifiers. They increase the signal of both transmissions and receptions based upon the configuration of the elements inside the antenna. Some are more powerful than others. The next important location is very near the tip of the antenna where the signal leaves the antenna for the air, our medium. The measurement taken here is the equivalent isotropically radiated power, or EIRP. It is the product of transmitted power, any connectors, cable loss introduced, any amplification, any attenuation created there, any imperfections, any voltage standing wave ratio problems where you have impedance mismatch between connectors and cables. Anything that goes into that will be a combination of what makes up this signal. Active amplifiers are going to introduce electric current into the cable to boost the power, and they're very useful if you have a long cable run between the transmitter and the antenna. In this scenario, we started with a 100 milliwatt signal, introduced 3 dB of loss, and then added 3 dB of gain to find ourselves back at the original 100 milliwatts or 20 dB of power. In the field, it is easy to convert everything to dB, then simply just add and subtract. So you don't have to worry about milliwatts versus decibels measured or decibels measured against an isotropic radiator. For example, 20 dB, which is what we're transmitting at our radio, minus the 3 dB of the 100 feet of minus 3 dB per 100 foot cable, plus the gain of the antenna of 3 dB will take us back to our original 20 dBm or 100 milliwatts. Knowing where to apply that knowledge in troubleshooting and implementation is of great importance because in certain regulatory domains, 100 milliwatts may be the most you're allowed to purposely put in the air. Basic RF math, the rule of the tens and the threes. You can use the rule of the tens and threes to quickly approximate RF loss or gain calculations. The base in converting milliwatts to dBm is that 0 decibels measured is equal to 1 milliwatt. Remember, decibels are measures of change, and in our calculations, they're referenced against a base of 1 milliwatts. So if we're starting with 1 milliwatt, there is no change, and our value in dBm will be 0. That's our starting point. 1 milliwatt is our starting point for referencing RF power, which references no change. With no change, the dBm value is 0. Here's where the rule comes into play. For every 3 dB increase in power, the milliwatt value is doubled. 3 dBm doubles our base value of 1 milliwatt to a value of 2 milliwatts. A value of 6 dBm would be the equivalent of 2 times 3 dBm. So the first 3 dBm doubles the 1 milliwatt base to 2 milliwatts, and the second doubles the 2 milliwatts to 4 milliwatts, and so on. An increase in power of 10 dBm multiplies our base value by a factor of 10 equaling 10 milliwatts. 1 milliwatt times 10 equals 10 milliwatts. An increase of 20 dBm would be 2 tens. The first 10 changing our base to 10 milliwatts, and the second 10 changing it to 100 milliwatts because it would be 10 times 10 equaling 100. A dBm increase of 30 milliwatts would increase our RF power to 1000 milliwatts or 1 watt because it would be 10 times 100. This is all nice and easy until you get into values such as an antenna with 12 dBi gain. That is 110, but no threes. These situations call for formulas to determine the exact power measurement. Remember, the rule of tens and threes is a quick approximation. In this example of 12 dBi gain, you could use 110 and 13 to get close to the real number. When using such values, always use the tens first and then the threes, just as in the name of the rule, tens and threes. Should you ever need to know your EIRP is within the legal limits, using such values, you can use an RF calculator, which uses the correct formulas, will give you an exact number, and you can find those for free online. If the tens and threes rule has you under the legal power limit for your region, you don't really need to do that math because you know you're legal. In the previous discussion, we focused on gain, an increase in amplitude or power. The rule of tens and threes can also be used for loss, a reduction in amplitude of power. For every 3 dBm of loss, the signal strength is divided by 2. We still use the same base value of no change or 0 dBm equaling 1 milliwatt. If a loss of negative 3 dBm is introduced by cable, connectors, an attenuator, or simply propagation, the signal strength is cut in half. So our base value of 1 milliwatts will become 1/2 milliwatt. If a loss of negative 6 dBm occurs, the equivalent of the loss of 2 times 3, the power will be reduced again by half to a value of 0.25 dBm. If the value is in tens, for example, suppose the RF wave transmitted by the antenna moving is through an environment and it must move through an obstacle that causes a 10 dB signal loss, the power of the wave before it strikes the obstruction would be maybe 1 milliwatt, and the obstruction causes a 10 dB loss. The result would be 1/10 of the original power. So it would be a much weaker signal. That's one of the reasons when we're dealing with relative values on client devices, you see them measuring signal strength in negative dBm numbers. Here's our example from earlier in this module. This time, the intentionally radiated power and the EIRP values are missing. Let's solve for them using the rule of the tens and the threes. Our access point is transmitting at 100 milliwatts. Well, we don't want to deal with a combination of milliwatts and dBm, so we'll need to convert the 100 milliwatts to a dBm value for our exercise. 100 milliwatts is equal to 10 dBm. If you remember our math from earlier, our base is 1 milliwatt, and we would use 10 times 1 to get to 10, and there'd be a second 10 to take 10 and multiply by 10 to get to 100 milliwatts. So 100 milliwatts is the equivalent of 20 dBm. Remember, 20 dBm is made of 2 tens. So now we have all of our values given in dBm. So let's do the math. 20 dBm minus the 3 dBm loss of cable equals 17 dBm intentionally radiated power. So we are purposely putting in 17 dBm into the antenna. Now we have to calculate our equivalent isotropically radiated power. What's that value? So we know we've got 17 dBm going into the antenna. The antenna itself, as you can see in the illustration, is a 3 dBi gain antenna. And here's a little trick. dBm and dBi, I can still use the numeric values without converting from dBi and dBm because we're looking at dBi as a change, and we'll come back with our dBm value. So I can just add the numbers and subtract the numbers, and I'll get a real value here. So we're adding back in 3 dB. So it's going to be 17 dB plus 3 dB, and that's going to equal 20 dBm, or 100 milliwatts of equivalent isotropically radiated power. That is a quick, even look at the rule of tens and threes. Quite often, you may run into antennae that are not 3 or 10 compliant. You may have something that's a 14.5 dBi gain antenna. Then you're going to have to start looking at real calculators for that. And you may not have an exact cable length equal to the loss per the specified distance. You also have cables with connectors and attenuators and lightning arresters and amplifiers and other things connected. So you may need to measure the power at the cable using some specific equipment made for that purpose to know exactly what's reaching the antenna. Then you can do the math for the IR value plus the gain of the antenna, and that will get you close to what's actually going in the air with the tens and threes. Or if it's not an antenna that is evenly configured with tens and threes for its gain, you would use an RF calculator and you would punch in the numbers and it would tell you exactly what should be coming out in the air. The received signal strength indicator value, or RSSI, is a relative value of the strength and quality of an RF signal being received by an antenna. There is no industry standard for calculating the RSSI value. Each chipset calculates how it was designed to by the manufacturer. Two radios at the same distance from the transmitter and in the same RF environments, subject to all the same noise and blockage, may display different RSSI values for the exact same signal. The 802.11 standard states that RSSI is intended to be used in a relative manner and that absolute accuracy of the RSSI reading is not specified. It is usually measured during the reception of the 802.11 frame preamble. The RSSI will be seen as negative dBm values. As you learned earlier, an RF signal weakens as it propagates. The largest portion of loss comes at about 5 meters away from the antenna of the transmitter. This loss is exponential, meaning the farther away the receiver is from the transmitter, the weaker the signal is going to appear to be and the RSSI values. In our previous example of RF math calculation, the EIRP was 20 dBm or 100 milliwatts. An intended receiver at a short distance away may actually have an RSSI value for that same signal of a mere negative 40 dBm. Relatively speaking, this is a weak signal compared to the EIRP. However, it's a great signal for Wi-Fi. Receiver sensitivity. The receiver sensitivity defines the minimum signal strength at which a data rate can be correctly received by a station. As stated earlier, receiver sensitivity varies by device and manufacturer. Vendors publish receiver sensitivity thresholds, and they are usually referenced to dBm. Remember that dBm is an absolute measurement of power. RF sensitivity thresholds indicate power limit of received power required to support operations. The stronger the RSSI value, the faster the communications can be. Different applications have different minimum requirements to operate and to be most efficient. Since the received signal strength is a measurement of power present in a received radio signal, some receivers need to be closer to the transmitter than others to work well. Receiving devices at different distances from the transmitter will receive the signal at different power levels due to the propagation and obstructions in the airspace. Due to the allowed industry variance in RSSI calculations, it is important to plan your wireless LAN deployments around the needs of the client devices. For example, some Wi-Fi phones need a received signal strength indicator value of negative 67 or better to work properly, while others require a value of neg 65 dBm or better. You need to research the devices used within your deployments and build the environments to support those devices and the applications that they are using. A signal-to-noise ratio, or SNR, is defined as the difference between the noise floor and the signal in dB. This diagram shows the signal strength over distance as a curve that has the best signal strength closer to the transmitter. The diagram also shows noise within the space. The noise tends to be the garbled up background RF noise or signals that come from everything around the receiver, including such things as the sun and stars, to man-made interfering devices such as Bluetooth headsets or remote controls. It is impossible to block out all noise in an enterprise setting, and it shouldn't be attempted because it's very cost prohibitive to do so. Low-level background noise is called the noise floor. The noise floor will vary from location to location based upon local interference sources, even within the same building on the same floor. The ratio of the signal-to-noise level, or SNR, defines the quality of the link. This is directly related to the performance of the network. Based on the SNR, the client and AP will negotiate a data rate with which to communicate. The higher the SNR, the better, because higher data rates can be used, increasing throughput. For good performance, the signal-to-noise ratio should be greater than 20 dB. And for optimal performance, it should be greater than 25 dB. To avoid noise issues, watch out for common noise generators such as microwave ovens, wireless video cameras, cordless phones, headsets, and even Bluetooth devices. You should especially be prepared for noise in the 2.4 GHz space, because many non-802.11 devices operate in that unlicensed frequency. All of these things are seen as noise. Imagine speaking to another person in a quiet room versus speaking to that same person on a crowded convention hall floor. The quiet room would have a high signal-to-noise ratio value versus the low signal-to-noise ratio value of the convention hall discussion. Signal-to-noise ratio is a very important measurement in determining the quality of the Wi-Fi environment. If your noise floor power levels are too close to the received signal strength levels, they may be corrupted or not even detected. To determine your SNR, measure both the signal and the noise. Then subtract the noise value from that of your signal. A common noise floor used in design is negative 95 dBm. If your signal in that area is detected at neg 70 dBm, your SNR would be 25 dBm. Remember that there is no industry standard for the calculation of the RSSI values by the receiver, as they are determined by the chipset that the device is using. It is of great importance when designing wireless networks to know the requirements of the intended client devices and applications. A deployment that works well for a laptop may not work at all for voice over Wi-Fi phones or location tracking. If you have a high noise floor, you may need to increase the transmit power levels remaining within the legal limits of your regulatory domain, or add more access points than initially thought needed to cover the space. Design is about the needs of the clients and the environment in which they must work, not just coverage. If the noise floor is not negative 95 dBm, but is stronger, you will need to account for this when setting transmit powers. Some of the most common RSSI values used in deployments are negative 80 dBm for basic connectivity, negative 70 dBm for high-speed connectivity, negative 67 to maybe neg 65 for voice, depending on the particular phones you're using, and neg 62 for location tracking. Always verify the requirements with the device manufacturer and plan your least capable devices as being in that area for coverage. You may see in the field and on the exams you take situations in which everything was fine during your design, during the deployment, but now there's additional noise for which you need to account in your environment. If you're not able to remove the noise, you may need to change channels or revisit your transmit power settings at different AP locations. Link budget. The link budget is an important step in wireless bridge design or outdoor meshing. You need to make sure that you stay within the legal transmit power and that your link performs as expected even when conditions may change. To do this, you account for all RF gains and losses throughout the entire link with a minimum RSSI goal defined. This goal of signal strength is the absolute minimum objective for the link to function as required. To calculate your link budget, you must account for the transmit power, cable and connector loss on both the transmit and receive sides of the communication, antenna gain for both the transmit and receive, path loss, and any other gains or losses in the system. When planning a link budget, there are some additional factors to be considered. We're only going to briefly describe some of these as they go beyond the scope of this course. Antenna height. This is based on the distance the signal needs to travel and the height of structures to which the antennas will be mounted. It's to overcome any blockage between the antennas. Line of RF site, or the Fresnel zone, which ensures the outdoor wireless point-to-point connections do not have any natural or man-made obstructions that would cause the link to have problems with stability. Fresnel zones are beyond the scope of this class, but they represent in the 3D space between the two devices, of which at least 60% of the zone should be free from any obstructions. If you do not have at least 60% free, then the link is deemed possibly unusable. Fade margin. Fade margin is an additional signal strength above the required link budget to account for expected but unpredictable signal fading due to environmental conditions. Earth bulge. If the distance of the link is greater than 7 miles or 11 kilometers, you're going to have to take into account the curvature of the earth, not just trees and trucks and other buildings that could be in the way, but the actual curve of the earth. Once the link is installed in the environment, you can determine the actual margin for the link, called the system operating margin. The fade margin is the planned margin for the link, while the system operating margin is the actual margin. Performing a link budget. Here you can see a sample of the information needed in calculating a link budget. We have defined our minimal goal for this bridge and link to have factored in a negative 15 dB fade margin, as we begin with a transmit power of 26 dBm. Once we introduce the transmit cable and connectors and all the loss, we would then be at 23 dBm. The transmit antenna adds 15 dBi gain, taking us to 38 dBm. Free space path loss, being our largest loss in every communication, is at minus 104 dBm, which takes us to negative 66 dBm. The receive antenna has a gain of 12 dBi. That takes us to a negative 54 dBm. Once our receive signal traverses the receive side cables and connectors, we lose another 3 dB for a received signal strength level of negative 57 dBm, which is a very usable signal strength given that location tracking would work at negative 62. Now, these power levels may or may not be legal within a given regulatory domain. This is just an example of how to calculate the budget. So any link you create still has to operate within the legal transmit powers and frequencies set up by the regulatory domain in which you are deploying your bridge. Online RF calculators. I mentioned these earlier, that you could use these. There are many of them online that you can use for free. So you can put in things like distance between the antennas, what you want for your fade margin. Lots of tools have even antenna maximum dimensions and distance to obstructions and things you can add in there. You can find lots of calculators online for things like path loss and the Fresnel zone clearance. Lots of these factors you can calculate with things, and it's really very important for bridging and meshing more so than an indoor network. After this module, you should be able to understand absolute and relative units of measure, use basic RF math to calculate RF power levels using the rule of the tens and the threes, apply the basic concepts of RF mathematics and measurements, as well as calculate link budgets, and understand signal-to-noise ratio and receive signal strength indicator values. This concludes Module 4 of the Ruckus Wireless Fundamentals course.